Good afternoon. I started today looking at the camera. We were talking about training neural networks before, and let's kind of summarize what we said. We said that the output of the neural network is corresponding to an input is determined by the weights of the neural network. And the entire concept of training the feed-forward neural network, as we presented, was determination of the weights. And the way these weights are determined is by a search process. And how do we find these weights? Well, we need to minimize some sort of objective function in order to do that. Last time we talked about the sum of squared errors as a method of minimizing the error. So we have our data, so we have our inputs, and then we have our outputs, and we have our index, and let's see, what index do we choose to use? P index is the patterns of the training set, so we have P, so this is 1, 2, all the way up to some value of P here. Then we have some sort of input string and a corresponding output string, so this would be I sub 1 and target sub 1. And this would go down all the way to input sub P and target sub big P. Now these are fixed. The data set is fixed. The data set is not variable. The data set is what you're trying to adapt to. So think of the data as actually being fixed in the training of the neural network. We have the neural network now, and we have the inputs which go in here, say I sub P. And then we get corresponding outputs. And the outputs are output P's, but what we would like is not the output of P's, we would like the target sub P's. The input to output mapping, as we said, is determined by the weights of the neural network for the input and the output. And the entire idea of training the neural networks is to determine the input-output relationship that gives you a good result. Now, the way we do this is we take the output minus the input and make an error out of it. We square it, and we sum this over all values of P. P is equal to 1 to, I guess, big P. However, this output minus the input, notice there's a bunch of outputs here. These outputs are actually parameterized by I. So this is I is equal to 1 all the way up to I is equal to, say, for example, I. And so when we perform this summation, we're also summing over the output nodes. So we're summing over all of the output nodes, and we're summing over all of the data in the data set. And the error, which we generate, is the sum of square errors, which is equal to this result. You will notice that implicitly this output is a function of all of the weights in the neural network. We're assuming that we have a fixed architecture. In other words, there's a fixed number of hidden neurons, a fixed number of weights, and etc. So the architecture itself is fixed. The way you choose that architecture is another question, but let's assume that it's fixed. If it's fixed, this input to output mapping is going to be a function of the weights. And we would like to have this output be equal to the target. And in order to characterize the error, the total error associated with the entire training set and all of the outputs is to perform the sum of square errors. And the sum of square errors is a function of all the weights. So we actually have a multidimensional function. It's a multidimensional function in a very high dimensional space, and every value of weight that you choose corresponds to a coordinate in this high dimensional space, and every coordinate has an error, and a sum of squares error associated with it. And our job in training the neural network is to look around this space in order to find the place where the error is the smallest. And it's a classical optimization problem. And there are numerous ways that one can do this. But that's the basic idea of training a neural network. So the only variables, again, are the weights. The training data is fixed. The weights, the architecture is fixed. The only variables, the knobs that we tweak in order to perform this operation, are referred to as the weights. Many times we can visualize this space. We can visualize this space, say in 2 dimensions, Here's weight 1 and weight 2. Of course, we typically have numerous weights, up to thousands of weights. And we can visualize this as a some sort of structure here. And maybe this goes down to a 0.2, this goes down to a 0.1. And so what we'd want to do is, the error is smaller here. If our entire purpose in life is to determine the weights which minimize the error, it turns out that's not our only problem. But if that were our problem, then we would want to choose this value of W, and this value of W, and whatever those weights are, the weights we would use in the neural network, which would give us the minimum error associated with the training data set. Does that make sense? So it's searching over this, what is referred to as the landscape, the error landscape, objective function landscape, is what we would like to do in order to optimize the neural network. Now, there's people that use their entire, I think I mentioned this last time, there's people that devote their entire careers to optimization algorithms of different types. In fact, I've heard at Boeing they refer to themselves as penalty function. This is a penalty function because you want to minimize your penalties. Penalty function artists. They actually paint different energy functions. And you'll notice this energy, I'm sorry, I said energy, this error function is not the only one that we could use. It works. It's a mean square error, and we know that some of the things that we would like to do is we would like to minimize this. And we like mean square errors, but that's not the only one we have to do. We could also choose, for example, the maximum. Which would be the max over all of P of the output minus the target. This could be another objective function which we used. And what we'd like to do is we'd like to minimize this. This is a minimax solution. So just like we would like to minimize this error, we would also maybe like to minimize this error. Now this error says that the maximum of the error corresponding to each one of the training data. So this has an error, this has an error, this has an error, this has an error. In fact, for a given set of weights, we could come over here and we could look at the error for each one of these. And what we would want to do is we want to choose the maximum error, and then whatever this maximum error is, we would like to minimize that maximum error. And doesn't that make sense as another possible objective function that one could use to train the neural network? And the answer is yes, we could use this also. So therefore, choice of the function that we use to perform a minimization is a matter of choice in some sense. And each of these has a different sort of property. Those of you who are familiar that took Professor Damborg's class will notice this is kind of an LP norm. This is an L infinity sort of norm, right? This is an L2 norm. If you've had this, if you haven't had it, you won't recognize it. But we can use an L7 norm or an L52 norm or whatever sort of norm that we would like to do. And that we're not even limited to those, L infinity and L2 sort of norms. But we can also do some things. There's one in the book where we look at an error corresponding to the cross entropy of the output with respect to the target, which is an information theoretic sort of response. Now, penalty function artists, what penalty function artists do, I am told, is they look at a problem like this, and then they craft, like an artist, a nice penalty function. How do you want to craft a good penalty function? Well, first and foremost, you want to have it give you a good engineering result, right? That's number one. Number two, you would like to choose a penalty function that is analytically and or computationally tractable. In other words, you don't want to choose something where you're going to have to really have a lot of problems determining things. And sum of square errors is very nice because it has a quadratic. Quadratics are classically very, very easy to manipulate. They differentiate nicely, right? We optimize by taking the derivatives, gradients. So it differentiates nice. Where is this differentiable? We did this before in here. Is that differentiable? Remember the fuzzy union? Maximum, we said that was differentiable? You don't remember that? Yes, you do. Okay, you're playing hard to get. I know. So this is differentiable also, but its derivative does not have a continuous first derivative, so it gets a little bit ugly. So you would like to be able to choose something which is tractable and hopefully has an easy landscape in which to manipulate. And the sum of square errors is very good at doing that sort of thing, although it isn't perfect and it isn't the last result. There are also other ways of doing things. There is actually, you can go from the sum of square errors. The square root of this is kind of an L2 solution to the maximum, which is a L infinity solution. You know the Ln norm? The Ln norm is, what is it? If you have a sequence, it's the summation is equal to 1 over n of a sub n. I better make that m to the nth, and then you take the nth root of it, I think. That's the L sub n norm. It's a lot like that generalized mean that we talked about before. And you'll notice that this, the sum of squares, is kind of like the L2 norm. And infinity, as we showed, is this norm. So one way to get from here to here is just choose the different values of n. I'm sorry, this should be capital N. No, alpha. Sorry, I'll get this right. That should be alpha. Another way to get from here to here is by doing the, in fact, a lot of neural network software has this ability. Well, let's call it the worst. And what this does is sum up the p is equal to 1 to, say, q, where q is less than p, of the worst errors, or the biggest. Worst means biggest. And we would, let's see, yeah, we would square this. Say biggest sub p. In other words, what we're saying is we come over here to this error, and for one case, we would just do the maximum. In the other case, we'd sum the squares of all of them. In this intermediate case, we would take maybe the 4 worst ones and add those together and try to minimize the sum of the 4 worst errors. Get the idea? And so you can see that's an intermediate step between these. So the point is there's just a glut of different techniques that we can do to choose the landscape of the error function that we minimize. Again, we use the quadratic because it makes a lot of sense, but more generally, we can, if we're more sophisticated, be penalty function artists, but we don't do that a lot. We typically use the square because that works very well, but it has some limitations. So let's look at our outline and see kind of where we're at. Supervised learning, we talked about this last time. We talked about continuous, discrete, and unsupervised learning being clusters. We talked about these objective functions, the sum of squares errors, the mean square error, the maximum error, which is the one we just talked about. The trimmed error is where you only take the worst of the cases and use maybe the highest 4 errors and sum those up and attempt to minimize that. So these are some of the different techniques for supervised learning. Of course, the gist, and what we haven't addressed yet, is how we determine the weights in order to minimize these errors. So let's now regress a little bit and go back to single layer networks. It turns out that single layer I'm just tripping all over my tongue today. Single layer networks were popularly studied in the late 50s and early 60s, and were primarily, the people very famous for them were Bernie Woodrow at Stanford University. He's currently a professor emeritus there. And Frank Rosenblatt. Now, Rosenblatt did a lot of work and was actually a very big promoter of neural networks. If you go back and you look at some of the early neural network history, you see Frank Rosenblatt being interviewed by the New Yorker. And, you know, the New Yorker, the magazine, popular magazine, kind of like a Time magazine, a Newsweek magazine, and he would be talking about all of these artificial brains and building up the hype, which many times is very destructive to fields such as this one. Frank Rosenblatt did much of the pioneering work, as did Bernie Woodrow in the early neural networks. Now, the problem with their early neural networks is that they use no hidden layers. And that's what we mean by a single layer neural network. It's a neural network with no hidden layers. They did this because they didn't know how to train it if it had more than one layer. They didn't know how to train it if it had more than one layer. And it wasn't until later, I believe in 1974, when Paul Werbos, who is currently with the National Science Foundation, published his PhD dissertation at Harvard University. He was the first to promote an idea called error backpropagation, which is used extensively to train neural networks. It turns out, like many great theories, I mentioned this previously, but like many great theories, it was discovered independently by a guy named Parker, another one named Rumelhart, who was at San Diego, and because he discovered backpropagation, got a job at Stanford, not an electrical engineer, by the way, a psychologist, the Department of Psychology. And those were the three, I think, that have popularized the idea. So let's take a look at the idea of a single-layer neural network from the historical viewpoint of Bernie Woodrow and Frank Rosenblatt. A single hidden layer network has no hidden layer. This is characterized on page 16. And let me just put up let me draw a picture of it. I think it's easier to draw a picture of it. We have a situation here where here we have the inputs, here we have the outputs. Now the outputs can be more than one layer. But we have the input, and these are the sensors, and we have a corresponding output. And they are uniformly connected. That is, every input node is typically connected to every corresponding output node. Now, each one of these output nodes is the neuron that we talked about last time. That is, if we were to look at one of these neurons, it would correspond to exactly what we saw last time, which was that we would be collecting the inputs over corresponding weights. And we would perform a summation operation on these and run these through a squashing function, and this would be the corresponding output. Now, in the more general layered case, this output could be a value which is a hidden layer value, which is subsequently transmitted to an additional neuron. But this is the simple result that we used here. Now, one of the interesting observations about this is that the input-output relationship here is as follows. If we perform this operation, we have the summation. Let's call this U sub I, or U. U is equal to the summation of, say, I is equal to 1 to I, corresponding to the number of inputs, of I, I can't use I, can I? I can use J, since we're not using square roots of negative ones. I sub J times W sub J. Right? That's what U sub J is equal to. Now, this can be written in vector notation as I transpose times W, since the W now can just be written as a matrix, and we are just having a single output. Assume one output. And then the actual state of the neuron, which we're calling Y sub I, is equal to the sigmoidal function operating on this U. So Y sub I is equal to the function operating on I transpose times W. Now, typically in a classifier sort of problem, what one does is the following. If one wants to make a decision between two things. Jockey players and basketball players. I don't know why that's so deep in my head. What one would do is they would look at the value of y. Now, y in general is going to take a value, an output between 0 and 1, correct? And one applies a threshold. What will this threshold determine? It will determine a point on the ROC curve, right? Because you could put the threshold down at the bottom, and you'd always be classifying one, so you'd never make mistakes with respect to them, or you could put it all the way up and classify the other one. So as this threshold went up and down, you would transverse an ROC curve. But nevertheless, you would typically choose a threshold. You would typically choose a threshold, and then the output would either be a 1 if it was above the threshold and a 0 if it was below the threshold. So if we look at this, however, we notice that the output, if we apply a threshold to this, this corresponds to where, well, let's look at the point of maximal ambiguity. That exists right where the threshold exists. Where the threshold exists, we have f of I w is equal to a constant, which is the threshold. Remember I said the points directly on the boundary were the most ambiguous? These are the points right on the boundary. So this is right at the threshold. A little bit one way, it's a basketball player. A little bit the other way, it's a jockey. Okay? So we have this situation. Now, this is a strictly increasing function. That is, the squashing function is. Right? A strictly increasing function, I can operate on both sides by the inverse of the strictly increasing function and maintain an inequality. In other words, if I want this greater or less than, if I want f sub I w greater than or less than some sort of threshold, that's the same thing that is saying that I transpose times the weight is greater than or equal to f inverse of the threshold. Does that make sense? In other words, I'm applying a strictly increasing function to both sides. I maintain the inequality, so my decision is not given. So this is equal to another constant, call it c. So my boundary between my decisions is given by this equation. I transpose w is equal to c. Now let's look at this. For a single neuron. If we look at I transpose W is equal to C, and above this constant is one class, and below the constant is another class, this is the same thing as saying that what? I1 W1 plus I2 W2 plus whatever, is equal to a constant. Let's suppose that the weights are fixed. We've trained the neural network. And let's suppose the weights are fixed. Now we're going to look at the way this neural network discriminates against jockeys and basketball players on the output. You will notice that this equation is the equation of a hyperplane. If this was 2 dimensions, it would be the equation of a line in 2 dimensions. If this was I1 and I2. Notice if we have I1 W1 plus I2 W2 is equal to a constant, that if we were to plot this, it would be a line, and that line would go through the origin. Do you agree with that? And in fact, in 3 dimensions, it's a plane that goes through the origin. In 4 dimensions, there's a 4-dimensional plane that goes through the origin. So no matter what dimension you go, we have a plane. Now what does this plane correspond to? That corresponds to the boundary, the classification boundary, which means on one side you got jockeys, on the other side you got basketball players, and we see immediately that this neural network that doesn't have a hidden layer is limited to being a linear classifier, just exactly like the Fisher discriminant. It can only take the classes and separate them by a line, just like the Fisher discriminant. Except it's even worse. It can separate them by a line, but that line has to go through the origin. That's even more restrictive. At least with the Fisher discriminant, that line could be floating somewhere. It doesn't have to go through the origin. But here the line has to go through the origin. Well, that's not good at all. We can take care of the line going through the origin by doing the following. If we had, let's just do the two-dimensional case. If we had an I1 and an I2, and then an input, which we're always going to call 1. We're going to artificially increase the dimension of the neural network by giving a third node, and no matter what the result is, no matter what the input is, this node is 1, and we collect the results here, and we go through the node. In this case, we're going to have I1, W1, plus I2, W2, plus this is going to have a weight 2. Let's call it W sub B. This is going to be plus W sub B is equal to a constant, this constant being determined by the threshold which is applied at the neural network. Notice all of a sudden what we have by including this additional node. We now have the flexibility of putting that line off of the origin, correct? So therefore now we have the case where the line, if we choose this node, the line can be off the origin. For clear reasons then, this is referred to as a bias, because it allows a flexibility in the classification discrimination of a neural network, because it allows that node to float off a line. And anytime you see a neural network, you will see these so-called bias nodes, and these bias nodes are very useful because of their ability to generalize there. But even with the bias node, we still have a problem, and that problem is that the classifier is a linear classifier. It can take points and it can draw only a line between them. This might be okay in terms of the iris data. We saw that it worked with the iris data, so you could probably get a neural network to do the iris data with that because it was linear separable, because we know it was, because the Fisher discriminant showed it was linear separable if you chose the right two irises. But there's other cases where if we did bushes and shrubs and we had a bonsai tree, so we had overlapping, and there's no way that a line could separate them, we get into problems. There was a classic book published in the actual literature came out in the late 60s, but the book was published in the early 70s by Minsky and Papert. Many of you probably are familiar with the terms. Anybody know Minsky and Papert? Minsky was the father of AI, one of them. But Minsky and Papert wrote a book which is still in print. And the name of their book was called Perceptrons. And many of the neural network historians actually point to this book as the death of the first phase of research into neural networks, because Minsky and Papert raised a very simple objection. Their simple objection was as follows. Many of the neural networks which had been developed at that time had no hidden layers. The Rosenblatt perceptron and Bernie Woodrow's neural network with no hidden layers called a Adeline. So they had no hidden layers. Therefore, they were linear classifiers, just like the Fisher distance. Minsky and Papert came up with an exclusive OR problem. And they say, let's take a look at an exclusive OR. Now, we all know what an exclusive OR is. Exclusive OR, we'll put a 0 here, a 0 here, a 1 here, and a 1 here. So what I'm trying to do is give different perspectives on data, where the zeros for the exclusive OR correspond to one class, and the squares correspond to the other class. Minsky and Papert says, look, you can't even train a perceptron to do a very simple exclusive OR. Why? Because there is no line which you can draw which separates the x's from the boxes, or the squares from the circles, right? Now, their point wasn't that we should all go out and try to do logic functions using these no hidden layer neural networks. Their point was, look, this very simple problem can't be solved by a neural network with no hidden layers. A very, very simple problem. Don't you think you're going to encounter lots of problems in this world with real data that are at least as complex as a simple exclusive OR? So it was a very compelling argument, and it dried up a lot of the funding in neural networks in the early 70s. Nevertheless, there's many things that we can learn historically. And we're going to look now at two of the single-layer networks. We'll look at the Rosenblatt perceptron. And the Rosenblatt perceptron was defined, he called it the perceptron, because it perceives, I guess. But it is that term has lived on to today, where we talk about neural networks with multiple hidden layers as being multi-layer perceptrons. The original term perceptron was coined by Frank Rosenblatt. Then we have the Woodrow-Hoff-Adeline. Bernie Woodrow and his graduate student Hoff published a paper which for years was also used for modem adaptation. A modem can be thought of as actually kind of an Adeline. Adelines, if you remember, the first day we talked about are used in the Concorde for control, the Concorde airplane, and so some of this research made its way into that airplane. So let's look at the Rosenblatt perceptron first, and look at the way that he trained it, that he chose to train it. The Rosenblatt perceptron had many inputs and one bipolar output. So here was the Rosenblatt perceptron, and it was a little bit different from what we've been considering. Yes, he took all of these inputs. Yes, he performed a weights with them. Yes, he summed up the product of the weights with the inputs. But what he did, instead of using a smooth function, is he actually used a binary output here. Actually, is a bipolar. His squashing function was just a step function. So his output was either a -1 or a 1. So he didn't threshold at all. He wanted to train this thing, and he assumed that indeed that he could train it. Now, the way Rosenblatt trained his network was not really by the energy function technique, although we could possibly pose it in that fashion. But he did the following. He looked at his training data. Say, here's the input vectors, and here's the target values. Now the target values for Rosenblatt were either 1 or -1. Because he was just interested in classification into one class or another using this square wave output. What Rosenblatt figured was the following: if he put in an input and it gave out the right answer, he didn't need to twiddle with those weights. Those weights were fine, right? However, if he put in something which should be a 1 and it turned out to be a -1, guess what he had to do with the weights? You want to make all the weights a little bit smaller, so that next time it would be pushed a little bit more towards a smaller value to give a negative value, right? Conversely, if you wanted out a -1, now if you wanted out a 1, what did I just say? If you wanted out a 1 and you got out a -1, what would you do with the weights? You would increase them a little bit. Conversely, you would decrease them a little bit, right? And that was Rosenblatt's simple training procedure. So he actually performed an update in accordance to the Rosenblatt learning rule.
Did he change them all?
Yes, he changes them all by the same amount. I'm trying to look for it. Okay, here it is. Delta W is equal to 2 eta, the target times the output. If the target was not equal to the value, and is equal to 0 otherwise. Now let's take a look at this learning rule. Let's see, T, I think there's a typo in the book. This should be a Y. Now, eta is a parameter which is part of the training procedure and is referred to as the step size. It is the amount that the weight is adjusted, okay? And so the concept, again, if the output is 1 and it should be a -1, everything is, the weights are correspondingly reduced, but you don't want to reduce the weights if the input is negative, right? You would like to increase it. So therefore, this takes into account the ability to perform that operation also. So we see that if an error is made, the weights are nudged in a direction which is going to give you a answer more close to the correct answer next time. Now, what might happen is you go through these weights and you say, oh, this one's okay, whoop, I got to adjust this one, oh, that one's okay, whoop, I got to adjust this one, and then you get all the way to the end. Or you might get all the way to the end, and guess what, you come back here and do the first one again, and maybe you've wiggled the weight so much that this is no longer good, right? So you might have to wiggle it again. And so indeed it is an iterative adjustment where you have to go through the data a number of times. There's a term going through the data one time which is called an epoch. And each time you go through the data, you go through what's referred to as a single epoch of training. And you would have to go through the data a number of times in order to train the Rosenblatt perceptron. There was an actual proof that if your original data was linearly separable in a high-dimensional space, if it was linear separable, that indeed the Rosenblatt training algorithm did converge. Okay, it isn't apparent. It makes heuristic sense that it would converge. Now let's see, delta.
Yeah, there's a sign error there somehow.
There is. Okay, how is that? Okay, this is Y, and this is the target. So if the target is not equal to Y, oh, I'm sorry, this should be I. It should be I. In fact, I wonder if we use X there. Yes, okay. Now in the book, I think this is called, this input is called X for some reason. We switched notation. But this is the actual value of I. Okay, does that help now?
Can you initialize the weights too?
Very good question. Where do you start?
Are they all the same? Are they random?
They're random, right? Typically, these would be initialized randomly. In fact, you wouldn't want to make them all the same. Why? Because every time you adjusted them, if you made them all the same, well, no, they would adjust because the sign SIGN of the input might change and knock this weight one way and this weight the other way. So they would separate.
So
Yeah.
the weights don't change uniformly if you're multiplying by that vector.
This is the change in weights.
Right. Is the vector I uniform also?
No, the vector I is the input data for your training. So this would be, for example, a jockey and a basketball player and another jockey and a basketball player. So the I's are actually the features, for example, the weight and the height of the result. And then we say T is equal to 1, this is a jockey. T is equal to -1, that's a basketball player. T is equal to 1, that's a jockey. Yeah.
Does your step size stay the same through all the different epochs?
In the most rudimentary case, yes, it does. And what happens is exactly the same result that you get in control theory for step size. You can envision this linearly separable problem with the plane or the line actually beginning to choose its orientation in some fashion, right? As it begins to wiggle back and forth as you go through the different epochs. If you make delta too big, if you make eta, the step size, too big, whoop, 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 it's going to go all over the place. You're going to get the equivalent of overshoot. Whereas if you make it real teeny weeny, it's going to go. Toop, 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 toop. So it's very similar to the control theory problem. Okay? I think that in the book they give you a typical step size. Typically, eta is between 0 and 1. A good starting value is like a 0.6, maybe half. Okay.
So, I'm sorry, the vector I is filled with ones and negative ones.
The vector I, no, the vector I is not filled with negative ones and ones. The output is binary. Let me go through it again. The input and the weights are floating point. The inputs might be, for example, the weight of the individual and the height of the individual. These are multiplied by these weights and summed up. And then a bipolar, I use bipolar instead of binary because we have a plus minus 1 here. This sum is subjected to this to give a hard decision as either a basketball player or a jockey.
So you read the vector I of the jockeys and basketball players, but it's actually...
This is the feature of the basketball
Features.
player. Right. You're right. I should have put basketball player over here and jockey over here and jockey over here. Yes. Yeah, these are the features of the basketball players and the jockeys. So again, this is the Rosenblatt perceptron. But again, as we have seen, this is a linear classifier. It can only separate basketball players and jockeys that are separable linearly in whatever dimensional space you're in, where you can cut the two with a plane. And the perceptron proof, actually, which was provided by Rosenblatt, actually showed that if, this was a big if now, if the original data was separable linearly, then this would converge over any value of eta between 0 and 1. Yes?
Will there be only a single feature at a time that we can input, or can we input?
No, we would actually put all of the features in with respect to time. We would put all of the features in, we would get a result, and then all of the features, notice this delta weight is a vector. So the first element in this vector is how much this weight is updated. The second element in this vector is how much this weight is updated, etc. So this is actually a vector notation. See, this is a vector here and a vector here. I should have a zero over that also in order to make it a vector. So yes, everything is nudged. If you have an incorrect result, all of these weights are adjusted to nudge it towards the correct result. And the degree of the nudge is given by this eta, which is the step size. And the step size is between 0 and 1. Typically. Any other questions on this? So it's a relatively simple concept today. Back then it was enormous. And Rosenblatt used this very effectively to do a number of very interesting results. So this was the Rosenblatt perceptron. I'm not going to go over the proof, but it is in the book if you're so inclined. I also want to talk about the Woodrow-Hoff adelines. The adeline that can't be right. Oh, ADA. Anybody seen the adeline? It's an acronym, kind of an acronym. What do they call it an acronym when you keep parts of the syllables? That's still an acronym? I don't know either. Okay, it's adaptive linear neuron. Okay, adaptive linear neuron, adeline. Guess what he called it when he had more than one neuron? You'll notice that for this Rosenblatt perceptron over here, how many neurons do we have? One. This is one neuron that's doing this learning, right? And the only thing we're doing is taking these senses and we are weighting these senses in such a manner as to make a decision. So the Woodrow-Hoff, like the Rosenblatt, is also a single single layer network with no hidden layers, and so it's a single neuron. Later on, Woodrow and Hoff expanded their work to a number of different neurons, and they couldn't call it Adeline anymore because the neuron is positive, is singular, right? So that's what they called it. You think they would call it Adelines, but Adelines would just be a bunch of disjoint single neurons. So they called it Madeline. One. Multiple adaptive linear neurons. So Adeline and Madeline were in Woodrow and Hoff's way of doing things. Now, Woodrow and Hoff actually used a soft squashing function. So here we have the same sort of situation. And we have weights associated with it, W1, W sub 2, W sub 3, W sub 4. These were summed up, and these were run through, these were typically run through some sort of sigmoid nonlinearity, although for a Woodrow-Hoff algorithm, you didn't have to do that. Well, let's say we did that. Ran it through some sort of squashing function that squashed it between 0 and 1. And then the output was something that which was either given a value of 1 or a value of 0. Now, as before, we have an output y, and this value of y should be equal to a target. So we would like to choose these weights so that the output y was equal to a target. Now, you'll notice that the Adeline has the capability of, and this is the Adeline here, the Adeline has the capability of actually fitting data. In other words, it can be a regression machine. The output is not restricted to be binary between a 1 and a -1. It can actually take on various values. So it could be used, for example, to predict the amount of rainfall tomorrow, which is one of the things that Woodrow did. He did weather forecasting with it back in the 60s. And actually trained it on historical data to do this weather forecasting. Now, for the case of Woodrow, we have an error associated with the function, and this error is equal to, let's just say, y minus t squared. And let's just suppose for now, well, no, I guess we can not do that. P, y sub p minus target sub p. And this error is a function of the weights. As we mentioned before, this error being a function of the weights corresponds to a landscape in weight space. So therefore we have in weight space, weight 1 and weight 2, and we want to find the minimum in some sort of fashion. I mentioned that there were numerous ways for us to find this minimum and therefore find the values of W1 and W2, which minimize the error here. One of the ways to do this is through the Woodrow-Hoff algorithm, which is very close to a steepest descent algorithm. Imagine yourself on a hill in West Virginia. I was born in West Virginia, so I like the hills there. And what you want to do is you want to find the lowest point in the hills. But you're blind and it's dark. What do? Because that's kind of where you're at here, right? You choose a value of weights out here, and you get a value out here. You know how far you are above sea level. You know what your error is here, right? But what can you do, if you know that error, to find the lowest point? One of the things you can do is kind of sense which way is downhill and take a step in that direction, right? That is basically what the Woodrow-Hoff algorithm does. It looks downhill and it takes a step in that direction. The question is, what is downhill, right? Well, downhill turns out to be in the, say, the W1 direction. Downhill happens to be the rate of change of E. Well, you notice, I'm sorry, this is delta W, and it's a vector because you have to have a direction associated with which way is downhill. Well, going downhill is proportional to D. In the W1 direction, it's proportional to minus the partial of E with respect to omega 1. In other words, you want a derivative, right? A derivative will give you the slope. And minus that slope will give you a step in the direction where you go downhill. And so indeed we have that. So an element of this in the W1 direction is a partial of E with respect to W1. The other one is the partial of E with respect to W2, etc. So if we determine all of these, and then we determine a step size associated with it, this gives us kind of a direction on how steep it is downhill. We still have to, just like in the Rosenblatt case, figure out what a step size is. We have to determine whether we're going to go downhill and take big steps or we're going to take little baby tiny steps. The control theory here becomes very obvious. If you take humongous steps, and here's where you want to end up with, you're going to whoop, 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 whoop. You'll eventually get there, but you have a lot of overshoot, just like in a underdamped control system. And if you take little baby steps, you'll get there, but it'll take you a long time. So intermediately, there are certain step sizes that will indeed get you to this minimum eventually. Now we can actually look at this error with respect to these different weights and come up with the Woodrow-Hoff training algorithm. Let's, for example, look at the error. Let's look at this error. This error with respect to W1, W2, etc., is equal to, let's see, the summation of P of y sub p minus t sub p. Let's square that. But this is equal to what? This is the summation of p. And what is the y sub p equal to? That's equal to the sum of the inputs, right? From the pth result to the ith, and then I better put that a j, sorry. J times the jth input minus t sub p squared. Now what I'm doing, I'm assuming that there's no sigmoid. In other words, the squashing function is no squashing function at all. If indeed that is the case, we have this result. Oops, this should be w sub j, right? This should be w sub j. So we have this situation now. How do we determine what's downhill? This is the error associated with our case of W. All of the inputs are fixed. That's part of our training data set. All of the targets are fixed. That's a part of our training data set, right? The only thing that we want to do is find in the landscape the value of W's, which minimizes this error. And I think if we use steepest descent, then what do we want? Well, in the W1 direction, we want the partial of E1 with respect to W1, right? That will tell us which way is actually uphill. We negate it to go downhill. So this will tell us which way is uphill in the W1 direction. So if we take the partial of this, we get the summation of P. Well, you notice something which is very interesting here is that all of the terms here go to 0 except for W1, right? All of the terms here go to 0 except for W1. So we're left with I sub P1 minus T sub P, and we get two of those because we're differentiating this, right? And let me do this a little more carefully. Remember the chain rule, which says you get twice whatever the result is here, times the partial of what's inside. And the partial of what's inside is, the partial of this is equal to I sub P1. Did I get that right? I think that's correct. In many cases, in fact, in the book, you'll find out that the error function actually has a half here. And it looks kind of artificial until you get to this differentiation point, because this half eats up the 2 and we just don't have to worry about it. Well, here is the beautiful thing about the Woodrow-Hoff algorithm, because this is steepest descent. What do we want to do? We want to take our new weight and we want to make it in terms of the old weight minus a small step downhill, or plus a small step downhill, which is minus eta times the partial of E with respect to W1. That's a small step downhill, which is what the Woodrow-Hoff algorithm does. And you can see now that it's simply by substituting this relationship into here, we have a very nice learning rule for taking small steps downhill, totally in terms of our inputs and our outputs. So it's a very nice relationship. Again, the choice of eta is one that you must make, much like in a control system, to avoid underdamping and to avoid overdamping also. Okay, any questions on that? Now what I have shown you is actually steepest descent. Because you will notice the following happens in steepest descent. In steepest descent, we have to go through an entire epoch. We have to accumulate our error, and then we take a step, right? Because you'll notice the summation in P performs a summation on all of the errors on the output. This sums over the entire database before an update is made before the step. This is steepest descent. The Woodrow-Hoff algorithm wasn't as gracious as this. What they decided to do was, let's not sum them up. Let's look at the first piece of data and decide on a step. Let's look at the second piece of data and decide on a step. Let's look at the third piece of data and decide on a step. So it didn't wait for the entire epoch to go through. It did it for every data. Okay? And it's very, very different results. In fact, one data point at a time is sometimes referred to as online trading, and this is actually the classic Woodrow-Hoff algorithm, was the online trading. One epoch at a time, let me say data point, I should have put a data point here. One epoch at a time is referred to as batch training, because one has to put the entire training data set in, sum up all over these values of P, and then do an update. Let's look at what happens for online training. So do you understand the difference between the two? With batch training, you go through the entire data set, you accumulate all the error, and then you make a tiny step. With online training, which is the Woodrow-Hoff algorithm, you obtain a result, and then you take a step. You obtain another result for the next data point, you take a step. Now, the interesting thing about the Woodrow-Hoff algorithm is that, in a way, it isn't apparent that it should converge. Because each time you go to a different data point, you are trying to minimize the error for that single data point without regard for the rest of the things in the list. So in essence, every time you go from one data point to another data point, your error surface is actually changing. So typically what happens is you get much worse jitter in the solution. Now we actually have a steepest descent solution in the book. Let's see if I can find it here, because this is a perfect place to show it. Of course I can't find it. Here we go. Okay, this is on page 164. Can we zoom in right here, please? Okay, good start. Can you zoom in here? Good. This is actually for a general perceptron, but it illustrates the point of the small step size versus the large step size. And this was actually done for an error surface which was parabolic. You can see, as I mentioned, this is a small step size going downhill. Now you notice these are concentric ellipses, so downhill is always orthogonal to the elliptical boundaries, right? So whatever is orthogonal. So you notice that right here it looks like going downhill is in this direction. So we go, whoa, always remaining kind of orthogonal to the through the contours. And yes, indeed, we reach the minimum. So this is with a small step size. Here we have a very, very large step size. And with a large step size, we begin to perform these crazy operations as we have here. Now, if I can find it, we also have a difference between steepest descent and the Woodrow-Hoff, which is very, very different. Okay, I might have to find it for you next time. I thought I had this bookmarked, but apparently not. Let me give you a rough idea of what happens. You've seen the steepest descent for the steepest descent convergence. If we were to have a similar sort of thing for similar error surface, and we were to perform steepest descent, as you see, may go to something like this, if we were to use the batch sort of training. Now, with the online training, we looked at every point. This would be a much more jittery line. We would look at the first piece of data, we would take a step, and you know what? That step might totally be out of tandem with where the rest of the data wants it to go. And so this step might actually be over here. You might get another one over here. And you get this very jagged, jittery sort of thing, which will also eventually converge to the result, but in a much more jagged sort of way. Because again, every time you update for a single piece of data, you're ignoring the rest of the data, and you're just trying to optimize for that single piece of data. So this would be online, and this would be batch. Now, the Woodrow-Hoff algorithm was actually used for years. I don't know if it's still used for adapting modems to telephone lines, wherein there was phase and amplitude distortion over the telephone line, and there needed to be a way where this coherence could be added up. And indeed, the steepest descent algorithm was actually used to adapt the modems. Okay, are there any other questions? Are there any questions? There haven't been any questions. Any questions? We should mention that in training these algorithms, the idea is to get from your starting point, which is typically random, and we'll actually get to some different algorithms for choosing good starting points. That turns out to be a part of neural smithing, of choosing good starting points to get you to this solution. And steepest descent is one way of doing it. If you talk to people in the optimization field, they will sneer at steepest descent as being an antiquated old way of optimization which no one uses anymore. It's a very interesting result. Very interesting comment. And indeed, they're correct. However, the steepest descent and the gradual convergence allows us to do something very nice in neural networks that can't be done or is more difficult to do using other techniques. And that is the idea of learning versus memorization. And let me just in the final few minutes kind of touch on that. Suppose that I had a neural network, and here was my training data. A single input, a single output. Here's an input, here's an output. So I would have a single input and a single output. And suppose here was my training data. Now I trained my neural network. There's some weights in the neural network. And I'm not going to show you the neural network because this is generally applicable. There's some weights in the neural network which allow me to do this training. And eventually a bunch of different types of weights give me zero error. In fact, I find out that in one case that I get just this beautiful result here. Beautiful result. And then I train again and I find out something else. Now, what is zero error going to be? That's going to be any line that goes through all these points, right? And I do it again and I find out, there's zero error. Okay. Now, your intuition says that first line is better than the second line. But in fact, both of those lines have zero error. And the question is, how do you know which one's better? Your intuition says it's the first one, right? But how do you know? How do you know it isn't the second one? It has zero error too. The thing is that you have not told your optimization algorithm enough to pick one line over the other. You said, I want a zero error, so both of those are solutions that have zero error. So we need to tell a little bit more, don't we? We need to do something else. There are different ways of doing it. One of the ways is to actually, in the error algorithm, or the error statement, to include another term which will assure smoothness of the result. That's one way to do it. Another way to do it is as follows. We're going to take our data. We're going to take our data and we're going to divide it into two pieces. We will divide it into so-called training data, and we will also have some data which we kind of take and set aside called test data. Now, if you think about the neural network, what we would like to do is we would like it to be able to recognize things that it hasn't seen before. If we successfully classify a jockey, and we can only classify the jockeys in our training set, nobody cares. You can do that with a simple table lookup, right? Rather, you want it to learn and have the ability to, when a jockey is presented that you haven't seen before, to have that classifier appropriately classify it as a jockey. Hence the difference between memorization, which you can only, which is what happens when you only learn the data, which you trained with, and the other one is learning, or the ability to generalize, to be able to successfully classify objects which you have not seen before. That is our true objective. And getting that zero error doesn't quite grab that concept totally, as you can see in this case. So here's what we're going to do. We're going to do the same thing as we did before, and we're going to have two curves. We're going to have one curve, which is this curve. I don't want to use green. Let's see. I guess I'll use this. We're going to use this curve. Now, this curve is the one that we have learned from the black data. And you'll notice something interesting. I've drawn it so that there is a little bit of error. Okay? There is a little bit of error. And that's okay. And now what I'm going to do is do that crazy data that goes through all of the black data exactly. So this one has zero error. So this dashed line actually has a smaller error than the solid black line, right? Now, how do I know that the smooth one is better? Well, what I do is I train my classifier, or my regression machine in this case, and I pull out this test data that I've set on the side. And I apply this test data that machine has not seen before, and I look at the error with respect to the test data only. And I look at the test data from the solid black line versus the test data from the dashed line. You can see that the error from the dashed line is going to be much larger than that from the solid line. So by saving this test data on the side, I'm able to train my neural network. Once I've done it, I'm going to bring out this data. I'm going to apply it to the regression machine, see if it looks at it successfully. If it does, I've learned. If that error on the test data is too high, then I've memorized. Maybe. And one of the interesting things you can do when training a neural network is monitor this. Remember with the epoch training? We can actually look at our training data as the epochs increase. 10, 20 epochs, 30 epochs. This is the pass through the data. Now what happens is that generally this error will decrease, because heck, you're going downhill, right? In fact, typically these curves kind of look like exponential curves, e to the minus x sort of curves. But what happens if you go too far and you have too many degrees of freedom, That's the case with this wiggly thing, too many degrees of freedom. You're going to start memorizing if you go too far. So how do you know when to stop memorizing? Well, you take that data that you've set aside, this test data, and every few epochs, or maybe every epoch, you see what the training data does. Now, the training data will typically be larger than the test data, but the training data will typically come down, and eventually it'll start to go up as the curve deviates from this type of representation to the more wiggly representation. Now, when this curve begins to go up, and many times, unfortunately, this is very flat for a very long period of time, which is okay. But if there's a distinct minimum, what you do is you stop here. And you say, right here are the weights that I want to use because I have learned the data as best I can using this structure. And if I continue to train, I'm going to start to memorize because things outside the training data set and my test data set are going to have a very large error. Okay? So this is something one can do with the steepest descent algorithm that one has more difficulty doing with some of the other optimization techniques. Okay? So that's one of the reasons that in neural networks we still use steepest descent sort of things, is because there's other things that we want to do other than to get to zero error. Okay, any questions? Okay, hearing none, we will see you next Thursday in 2 days.